So yesterday we were discussing about full integration. Particularly, Michael Wegener mentioned that how much it's better from technical point of view. And it's really sometimes in ideal circumstances is the best way to go, full integration, tight integration. However, often the circumstances or requirements or priorities of a project are not satisfactory for full integration. And today I am going to present you the work we have done with Rolf in University of Maryland at the National Center of Smart Growth for Baltimore-Washington region, where we have a lot of diverse models, and we wanted to couple them. So we have explored various options of model coupling, and full integration was one of them, but it was not the most appropriate one for our purposes. So first, just to present our modeling area. So it's a Washington-Baltimore region, which includes Chesapeake Bay, which is the largest estuary in Northern America. The length of the coastline is longer than entire US West Coast. One important factor for this region is that the land-to-water ratio is 14:1, so the land use has a big impact on bay health. And it hosts US capital, Washington, as well as metropolitan areas like Baltimore. So there is a lot of competition between interest among agriculture, land use, urbanization, and transportation. So from that sense, this is a very interesting study to explore. And there are a lot of driving forces. Of course, population increase, sea level rise, climate change. You can see the forecast of 100-year flood event, which will have, in case of 1.1 meter sea level rise, and you can see Annapolis, which is the capital of Maryland, how much it will be affected. So there are a lot of interconnected issues, and this type of issues demand integrated decision-making and integrated modeling. At the center of national growth at the university, there are several models used to deal with this type of issues. These models, particularly presented here in this slide, we have economic projections from different sources. We have transportation model, Maryland statewide transportation model, which is officially used by transportation authorities in Maryland. We have silo model, which is one of the core models in the system. And we have emission models, building emissions, mobile emissions, and finally, we have water quality and land cover models in the system. But these all models were developed in different organizations, like MSTM, Silo. You can see the characteristics of the models here. And these models were developed in different environments using different programming languages. And they have also different licensing requirements. Most of the models are open source. However, particularly the MSTM is based on Cube environment, and it has some licensing restrictions from CityLab. And you can see also how long it takes to run each of the models. So this shows how diverse were the models we were trying to couple. And because all these models are used by different agencies, we didn't want to change the model source code because, for example, CBLCM, which stands Chesapeake Bay Land Cover Model, is developed in USGS, and it's continuing to develop. So they are constantly using it, constantly updating it, and we didn't want to do any changes in the source code ourselves because we knew that if we do some change, people in USGS may be not happy about it, and they may not consider our changes, and they will continue to use their own version. So that's why one of the requirements for our coupling was that we need to keep the models as they are. Luckily, the models we are running has kind of sequential flow. So for example, we run our silo model from 2001 to 2007, and then we use the output from silo from 2007 for our transportation model. And then the output from transportation model goes back to silo, where we can already forecast for another period, till 2030. Since 2030, we already feed silo output to other models, like, again, transportation model, but also mobile and building emission models, as well as the Chesapeake Bay land change model, and so on. So here in this table, you can see how many times each model actually run. So actually only silo is here the dynamic model. All other models are static model running just for particular time period, a time step. And this shows actually the summary of data exchange between the models. Again, you can see the core of the model, silo, coupled with MSTM. And this is the only case where we have this dual kind of the feedback between the models. Silo feeds MSTM, and MSTM gives data back to silo. All other models are using output from silo or MSTM, but they are not giving back any other data. So before starting the coupling, we started to explore what are the requirements for our project for the coupled integrated system. So these are the key requirements we came up. So first of all, as I mentioned, we wanted to be able to develop models independently and then be able to plug in them easily. Reusability was one of the requirements. We wanted to have friendly user interface, of course. We want to minimize manual data transfer, if possible, eliminate it, just to do automatic data transfer to avoid any errors. We don't want to change any code of the models. As you have seen, the models were developed in different programming languages, so our framework should support connection of the models developed in different languages. And it should be able to deal also with different licensing requirements, with open source or Cube license, for example. And because most of our data sets were spatial, and we have used a lot of GIS and maps, so we wanted to have compatibility with GIS software for easy visualization and spatial analysis. And finally, cost and timing also were some restrictions we wanted to take into account. So we have explored several coupling methodologies, and we came up with this paper from Brandmeier and Karimi, which actually presented the coupling methodologies for environmental models. And in this hierarchy, each layer has the capacities of the layer below, but adding some new functionality. So in my following slides, I will talk briefly about each of this layer. So the most basic level of coupling is manual data transfer, where two models are separate. They each have their own user interface, and user actually run the model and then manually transfer data from one model to another model. So this is the basic, least costly approach, but this is error-prone, and also if you need to do a lot of data exchange between the models, is not very reliable and it's not very feasible. Loose coupling is about the same, but the data transfer is done already automatically. So again, the models are separate, they have their own user interfaces, but here already data exchange is done automatically. Then there is user interface coupling, where there is one common user interface, which is kind of umbrella of models, and this integrates the models within that interface. There is data coupling option. I think Alistair mentioned yesterday that the database can be common and the data can be saved into the same database from different models. So this is that approach where we have one database and models are separate, but still saving the data into the same database. Embedded coupling is this tight integration when one model is embedded into the other model, or they are both embedded into one general software. So this is tight, full integration. And finally, there is this tool coupling, where some engine or library is used to couple two separate models. And there are different frameworks, different coupling tools were developed to deal with this type of coupling. particularly, we have explored some of these tools, like Open Modeling Interface, OpenMI, CSDMS, ESMF, and others. But initially, we started to actually consider OpenMI and then CSDMS for our project, and we actually started to work on this. But later, we found out that these approaches have their requirements. For example, they support particular programming languages, like OpenMI, although in their website they were saying that they support Java, but there were no much efforts done to implement the Java version of OpenMI. So we got a stage where we couldn't implement OpenMI for Silo because the Java compatibility was an issue. CSDM has better support. They have a big community worldwide. However, again, in case of CSDMS, there was a requirement that the source code of the models should be changed. Although the changes required were not big, but again, you need to implement some specific functions into your source code in order to make it CSDMS compliant. And this was something which we couldn't do, particularly for some of the models, because we don't have access to source code, or there were some requirements we didn't want to do. And I don't hope that you will read this. This is from Brandmeier and Karimi paper, giving the advantages and disadvantages of each of the models. So there's a lot of interesting comparison. If you are interested, you can check the paper. But at the end, looking all this and exploring all different versions, we came up with our version of loose coupling with shared user interface. So actually what we have done, we have used Python as a wrapper for our models, and then we have used ArcGIS Model Builder to have a user interface. So Python wrappers were included into ArcGIS, and the models were implemented using ArcGIS, and the data exchange was done automatically using Python. And why Python? Because it has very nice libraries, for, particularly for scientific programming, for modeling, for visualization and parallel computing. And also Python is very good with language interoperability, and sometimes it is used to glue other programming languages. Like there are specific libraries for MATLAB, R, Excel, Fortran, C++, and many other languages. And of course, it runs natively on Windows, Mac, or Linux, so it was very relevant to the type of models we are dealing with. This is just an example of this process, how the link was done. So the hexagons here, you see, represent the wrapper developed for particular model. Like the first one is a wrapper developed for Silo. The blue icons showing the data input, the green icons showing the data output from the model, and then you can see how the output from one model is transferred to another model. So in this case, we have transferred some data from Silo to CBLCM. So it's Python wrapper. The outputs mostly are in CSV format. But as you can see here, we have some intermediary tool here, Silo to CBLCM, which actually adjusts the output from Silo to make it usable for CBLCM, because it's rarely you can directly use the output from one model to fit the other model. So there is some data manipulation or adjustment necessary to do, which has been done here in this case with Silo to CBLCM tool. So this data flow actually shows what has been done for that particular transfer of data. Silo gives outputs in household and employment by transportation zones level, while CBLCM requires household employment by urban and rural areas and by county level. So actually this tool used the input from Silo and transferred it into the format required by CBLCM. This is how they look. Don't worry about it. And this is the final system we have got so far, and we have left our colleagues in University of Maryland with this. and Rolf came to Munich, and I escaped to Dublin. So now, so now they are struggling how to figure this out. But it is not as complicated as it may be seems. So it's just different models and different input-output, and you can see how they fit each other. So the benefit of this approach was that there was no need to change any source code. We actually just wrapped the models into Python, and then it was possible to include in ArcGIS. We could run models developed in different programming languages. It's very easy to add more models during the time. General user interface, although it seemed complicated, but it was very intuitive and was showing how the data is transferred between the models. And we could use rich visualization and spatial analytic capabilities of ArcGIS. And it's easy to implement because the wrapper structure are basically very similar. It just needs a few adjustments for new models, so it's very easy to implement. But of course, there are some limitations, which we realize. The parallel model runs and the dynamic data exchange are not supported. Model processes run independently from each other, and data exchange between the models are done by file transfer, so there is no in-memory data exchange. So during this process, we realized that in some cases, it's much better to have loose coupling. In some cases, it's much better to have tight coupling. And this is the graph Rolf composed for our paper together, where you can see where it is preferred to have loose coupling versus where it is more preferred to have tight integration. Like if we have frequent information exchange between the models, and there is bidirectional information flow, this is when tight integration is worthwhile, the efforts. But when there is one directional information flow and there's occasional or rare data exchange, then it's probably better to go with loose coupling and don't waste much time on tight integration. So this is the part we have done so far for Washington-Baltimore region. So you can see all the models coupled here, and this data transfer is now done automatically. But we have discussed what other models we can add, and there are a few options, particularly USGS use water quality model HSPF, which actually use data output from their land cover model. And currently, they just feed it manually. They just run CBLCM and then pass data manually, and then they run HSPF. So we thought that it will be good for our framework to add HSPF here also. And then there's another group working in Maryland who use ChessROM estuary physics model, which uses the data from HSPF. So this was our next step we are thinking to link. And finally, ChessROM feeds some habitat models, which are used to evaluate the habitats in Chesapeake Bay. So this is one link we are thinking to develop in near future, and we have submitted a project proposal to some funding agencies in the US, and hopefully, if it is successful, we will be able to implement this part too. The other part was using the already existing work with Silo MATSIM integration to link this with health impact model. As Rolf yesterday mentioned and Kelly today mentioned, the health impact model developed in Cambridge by James Woodcock is particularly one of the models we are interested in. And it demands individual level data for pedestrian and for bike users. And we are hoping that with the help of MATSIM, we will be able to implement this link. And if we get one air quality model, which can use the data from our building and mobile emission models, this can provide the air quality information required by item. So this part also will be implemented. So this is so far about the work done for Baltimore-Washington region. Before I pass my next slide, just because I'm going to talk about Dublin in the next few slides, I want to highlight here what I'm considering to do with Dublin case. So as you know, there is this ongoing work with MATSIM-Silo collaboration and MATSIM-Silo integration. And Dublin was one of the case studies of this new project Rolf has successfully got recently with his colleagues in Munich and Berlin. So we are hoping that we will be able also to implement this type of integration for Dublin. First having Silo with MATSIM, and then potentially integrate it with health impact model for Dublin. So this is the piece I am focused now to do for Dublin application. And this all work I presented is published by Rolf and me in Environmental and Planning B. So if you are interested about more details, you can take the paper. And now about Dublin. So now I'm back Dublin, and I'm thinking how to use these skills I learned in US. And some of you may know Dublin has an issue of sprawl, and it was actually indicated as a worst-case scenario for urban development by European Environmental Agency, and it was brought as an example that other European cities should avoid. So there is this issue planners have in Dublin, and they want to use some evidence-based stuff to have better decisions, and this is where we are trying to help them. And in Dublin, before I moved to Maryland, I used to work with Model Moland, which is a European Commission RICS model for land use. And it's actually cellular automata-based model, which has 2 levels, macro model. Macro model has the global level, population and employment forecast, and then it has regional level, social-economical information, and then in micro level, it uses cellular automata-based land use model where it has neighborhood rules, and it uses transportation zones, accessibility, suitability, and zoning maps in order to forecast land use change from year to year. So this is actually the stages Moland passed during 1 year time step. And here you can see how it looks when you run. You can see the year changing at the top left corner and land use changes, and this pink area is residential areas growing in Dublin region. So we used Dublin extensively we used Moland extensively for Greater Dublin region, and we had successful collaboration with Dublin regional authorities. They asked us to run several scenarios, and lucky for us, the scenarios output were fitting with the ideas they have about the region in future. So they were happy enough to include our work as an appendix in their planning review guidelines. So now there's another group working in University College Dublin dealing with source loading appointment model. So actually this is water quality model where they use land use as one of their input data to forecast the nutrition and phosphorus losses to surface water. So now I'm thinking to link these 2 models using the same technique we have applied in Maryland. So this is the input data provided for SLUM model, this water quality model. So they have direct discharges as one of the inputs, but they have diffuse nutrient sources where they have these land use types, and each land use has its different input for the water quality. And this is where Moland output can provide some information to this model. And I'm hoping that in the next few months, we will have some results how these 2 models work together linked with this Python and ArcGIS coupling method. So this is how we are planning to organize this data exchange. Yeah, I think that's it, and I want to acknowledge my colleagues in University of Maryland. You can see some of them here in my farewell lunch. And of course, Rolf, this work has been done with our tight collaboration, and you can read the details in the paper. Thank you.
Good. So floor is open for comments, feedback, discussion. So may I give it a start? So you're implementing now something similar in Dublin,
Yes.
meaning that, well, let me put it this way. It's interesting because, so we worked on this project together in Maryland. Now you went back to Dublin and you implemented another wrapper. I went to Munich and I abandoned this approach because I wanted to have something that's integrated in one software. So your conclusion is that working with a wrapper, the benefits exceed the cost of data transfer and model maintenance. Is that a fair conclusion?
I think it depends on the models you're trying to couple. Like in your case, you have ModSim and Silo both developed in Java, and you have this great opportunity for tight integration, which makes perfect sense. In our case for Dublin, Moland model is commercial. We don't have access to the source code, so unfortunately we don't have that opportunity. And the SLAM model is open source and it's based on ArcGIS. So it seems it's more possible to use loose coupling approach we have applied in Maryland. That's why. And also the Marie Curie project, I was funded to do this research in US. One of the goals was that you learn something outside of Europe and then apply that technique in Europe. So this is another reason I'm trying to use the same technique to have some comparison for the sake of my fellowship also.
So it sounds more like a necessity than the preferred approach?
I mean, for Moland and SLAM, I don't see any alternative because we don't have access to the source code of Moland.
Yeah.
So,
and if I may, one more question that came to mind when I looked at your slide. At the beginning you said the modeling suite in Maryland takes 23 hours to run. Do you have any sense for how much faster it might be running if we had gone through the effort and rewrote everything in one language and did a very tightly integrated model? Would it have made a difference to the runtime? You have a sense for that?
I don't think so that the difference will be very essential, because what we have here actually, like when we use loose coupling for this model, the only time we lose is this data transfer when you save data as a file into the system, into the hard drive, and then copy the file for another model. So this proportion of the time waste on the saving output and then copying it is not comparable with overall runtime of the models. So with tight integration, I'm sure we will save on this data exchange part, but it's not the significant part of the overall model run. Of course, some of the models like BAM is developed in R. Maybe R is not the most fastest language to use, but BAM takes only 30 minutes. So even if we implement BAM in Java, we may save, let's say, like 15 minutes. So again, I think our most, like we have MSTM and Silo, which are the most time-consuming models. And I think Silo we have already optimized as far as we could. And for MSTM, I'm not sure if in Java it would work much quicker. So again, it depends on the implementation,
Yeah, okay, so it's not so much a runtime issue in this case, Any other comments?
So in your Python script, does it run this entire system and run it through time, or does it mainly just grab the data from each one of these and make the transfer on a more or less ad hoc basis?
So let me go to this slide with, not this side. Okay, so each Python wrapper works separately just to grab the output from one model and then transfer it to a particular folder where it will be required by the next model. And then in ArcGIS model builder, we use precondition saying that unless this model is finished, this wrapper in this case is finished, don't run this model. So it actually when you run one model, it needs to be completed, which means that it passes all necessary output data to all required folders, and then it triggers the next model, and then the next model runs.
Yeah, I have kind of the same question that Rolf has. You know, how much of the time is actually spent taking data out of one format and putting it into another? Because in Oregon, we spend 20% of our time, you know, moving data from one system to the next. And part of that was intentional because we wanted people to honor the interface and not get so balled up in worrying about passing binary things or serializing objects and moving them. That allowed us to have developers in different places working on building different models, and they just had to respect the contract with respect to the interfaces. But it makes it inefficient. And so I'm wondering, you know, here, how much overhead is imposed by moving data between separate models?
It depends how much data manipulation you need. Like in particular, the case for, in this case, when we need data from silo to CBLCM, you see this part? And actually, the next slide, which I haven't talked much about, these are all the steps you need to do this data transfer from silo to CBLCM. So if you do this every time manually, it will take probably half an hour to do if you know the steps how to do it. But not just the time waste, it also error prone. If you miss one of the steps, if you kind of don't use the proper layer or something, you may continue with wrong data without realizing that your data was wrong. So it may give you some output which you are not sure. But in this case, when we have used this automatic data transfer, we have checked it several times to be sure that this data transfer process is correct. And then we are sure that this is done properly. I think one of the benefits is just to avoid these mistakes which manual data transfer may bring.
Thanks. First, I think just a comment. I mean, it struck me, we've talked a lot about integration and coupling and all sorts of, and it just strikes me that as much as we hate it, I suspect loose coupling is going to be with us virtually forever. I mean, I think this illustrates it, just the sheer number of different kinds of models we want to link together. And, you know, unless MatSim or something wants to start modeling, I don't know, water and energy and, you know, who knows what all else in one monolithic structure, I think, you know, there's domain experts in these different areas developing these models. So I think, as I say, like it or not, I suspect this is a practicality going forward. Anyway, the other, a completely different question, which we haven't addressed at all, and I don't even see us in our community talking about all, including myself, is the question, as we do couple different models together, whether anybody is, there's one thing, the interface, yeah, if you're passing an integer, it's got to be an integer. But the fundamental assumptions in different models, how compatible are they? I know I saw a PhD student a thesis many years ago, was worrying about, there was a forestry, they're micro-simulating a forest, and again, they're coupling different models together, and the big concern were there, does model A make fundamentally different assumptions than model B? And so we can succeed in passing data from one to the other, but does in fact make any sense to couple these two things together? And it just suddenly, something I hadn't thought about for a long time, but I wonder, is there an issue here that, you know, different levels of aggregation, different assumptions about behavior, you know, different values of time, I mean, whatever. Is anybody ever worrying about these things, or is it not an issue in this case?
No, it's a very valid point, actually. And of course, I think I read a paper by Alexei Voinov about how it's called intergrosters, when he makes the point that you may have very properly technically linked models together. From point of view, the software, it's ideal, it's coupled, but if these assumptions are not taken into account, this will bring some results which are nonsense or not viable. That's why I think it's a very important point that theoretically you must be sure that these data are comparable between the models and can be exchanged. I don't know if you have any points.
Any other comments? Other experiences? Do people mix models? Do people? I know, like Kai Nagel, you said you stick with one with one model. Do other people mix models? Is this common? You say you do.
Well, in a trivial sense, well, not trivial, but in a very straightforward way, I mean, our Tasha model or our XTMF-based, activity-based model interfaces with EMI. I mean, we don't write our own, and with MatSim. So that's a loose couple. We pass files back and forth. Yeah, and so, that works not badly. I mean, and to a certain extent, that was a design decision going way back, that there's a huge amount of network modeling going on in the world. We didn't consider ourselves experts in that, and we didn't want to reinvent the wheel. So by design, we really thought that we would always be coupled with a network model. Now, at some point maybe we say, well, we don't like those models and we don't like that coupling, and we'll have to bite the bullet and write our own network model. But I wouldn't want to have to do that. So as I say, I think it's fine to say let's integrate, but and talking out of the other side of my mouth, I've often said that, but I just think as a practical matter, I think this is a problem we're always going to, or it's a question we're always going to ask: is it worthwhile building that into our integrated piece of software, or do we couple with a pretty good model that somebody spent a lot of time working on? And I think, in our own field, the transportation, the network modeling versus kind of the rest of the demand modeling system is a classic example of that.
Yeah, kind of following up on what you were saying, Eric, I mean, I think that early on there was EMI, and one thing I liked about M was the fact that they had these fundamental objects. You had matrices, you had networks, and you had functions, and you could build anything you wanted out of them. But of course, they were only good for things that dealt with matrices and networks. And so when we were talking about designing TRISO, the model in Ontario, kind of borrow from the MatSim design, thinking about, well, if I'm using individual agents and everything else like that, then all of a sudden it makes going from one level to another very simple. And in some cases, we have actually built models in a microsimulation framework that don't necessarily need to be in a microsimulation framework from a behavioral standpoint, but from this whole level of integration, it makes life so much simpler and reduces so much of the error in translating data from one level to the other that it becomes compelling to do it in a microsimulation approach. Even though we still have to deal with all of the stochasticity and all of the stuff associated with that we just rather not even do, to me that's a really compelling reason to do it that way. And that's why we in Ontario we said, well, a foundational element has got to be the synthetic household pinpointed at a location, and it's a member of all of these different pieces of geography. And the same way with firms and everything else like that, because it just all of a sudden makes the, moving between these different models so much easier. And then Eric's got like a colleague that works in environmental processing models, so if we can easily give something to her and she can take it off and go do something else, and in my mind, that's at least as important as all these other considerations that we've talked about in the last couple of days. Because in the end, I don't want to spend 25 or 30% of my code time, which seems to translate to 80% of my coding time, just thinking about how to move data between these different things.
Actually, just remind me, I wanted to pick up on one of Kai's comments about how important he's come to believe the population synthesis is. And I think that's a very, very telling and insightful comment. I mean, I think because that is, first of all, I think it is very important, but that is a unifying piece of data that we can build all sorts of things off of. And I think you know, at the moment, we have a population synthesizer, the province has a population synthesizer. We've just gotten the code. I mean, there's going to be one population synthesizer for Ontario, whether it's the Toronto model or the Ontario model, and, you know, at least that's one piece of integration that we have that makes absolute sense. And so I think thinking about that your population base, your fundamental representation of your people, of your agents, is common across a number of platforms. I think that would be a huge step forward in itself.
Thank you. Yeah, I love that comment, because that's really, I hated the integration in Maryland so much because it was so much work to transfer, to write methods to transfer data, like the link from the land use model to the land cover model. We had to aggregate by counties. It had to be written in a certain order in which the counties were written. It was so painful. But I like this comment that you say, well, once it's microsimulation, once it's microscopic, and everybody just grabs the microscopic data, we get rid of this problem.
I think the takeaway for me is that, you know, it's 2017 in a few weeks, and I just don't believe that that you should be building any kind of model except using kind of the Matson metaphor for anything else that we're doing from now on. It's just so compelling to be able to move data and to take the agents and put them into different environments, which we don't really do when we do agent-based modeling, you know, like up at the lab that we do. You know, they're kind of situated in an environment, and they communicate locally with everything else, and it's really hard to change the environment. But, you know, now we finally can, and we need to start casting our models that way. And when we do that in a consistent manner, it'll make talking about models in a meeting like this a whole lot easier. It'll make exchanging data between these models a whole lot easier. And I think it just takes away that one design thing that we all struggle with. And I really hope we all move that way. I really do.
So, I guess the contrarian view. Well, not exactly. But when you were talking about mixing models, what came to mind for me is, like, for example, for metropolitan planning organizations, right, that runs what we call production models, right? They're regional models, and they use them to evaluate their regional plan, and they have to do it every 4 years, and so on and so forth. And so the regional model, the transport model, is just one piece of all the modeling they do. So they typically start with some regional economic model exercise, and then they move on to land use and allocate all that growth into small zones, and then they use the transport model, and then they do emissions, and some of them now are starting to do health indicators and whatnot. And so when we look at those things sort of in the way in which we've been talking about, we think of them all as a single integrated model thing with feedbacks, and that happens for sure. But what we miss sometimes is that in the exchange of data between one model and the next, it doesn't happen automatically. There's a lot of scrutiny from the agency and from the regional partners and the cities as to what the economic forecast is going to be like, and then what the land use forecast is going to be, and then what the transport and so on and so forth. And so even though we could integrate all the models, in reality, they run sort of in a broken fashion, because there is a lot of analysis and value and politics and whatever that gets inserted into the forecast in between what the model produces and what then gets fed into the next model. And I don't, at least in a sort of practical context, I don't see that going away, because among other reasons, it sort of requires political players to give away their relevance, so to speak. So.
Well, I don't disagree with that at all, but I think that you can have any model you want, and you can operate on that with any kind of model you want. The nice thing is that it just organizes the data in a way that makes the data exchange. But yeah, you could still leave the same sort of models the way they are, I think. You just spend a lot less time thinking about how to move data between them.
I really think that our lives would get a lot easier if we could agree on our fundamental units of exchange. And if we add persons to that, I mean, I think OD matrices are established and networks with links and nodes are also established and they will not go away. But if we could say lists of synthetic persons with attributes is also a fundamental unit of exchange, I mean, a possible unit of exchange. I guess we also have zones, that mean polygons or something. Yeah, so if we could just agree to add this, and then, I mean, I just looked, there's OMX, there's your PB base classes, but I can't see anything that's about person records, so it should be in there. Yeah. And if we could just agree to add that, doesn't mean that we have to use it. I think our lives would just become a lot easier.
Okay, thank you.